So hello. Um, why don't you start? So welcome to this async interview. Why don't we start by talking a little bit about who you are and what you've been doing, and what projects, and then we'll go from there, I guess.
Yeah, for sure. So my name is Eliza Weissman. I'm at HawkW, like the bird, on GitHub, and at MycoLiza, MycoLiza on Twitter. For anyone who has seen my internet presence or my pictures of my cats or bad computer jokes or whatever it is that I post on Twitter. I am a software engineer at Buoyant in San Francisco, where I work on Linkerd, which is probably one of the largest open source futures O.1 code bases. Probably us and TIKV and maybe a couple of other projects. And I also work on, I'm on the Tokyo core team, I suppose, which we have only sort of started to formalize. And I'm also the primary maintainer of the tracing crate. And I've been writing Rust a little bit for the last 5 years. I started around Rust 1.0. I was in college, and at the time I was really interested in writing operating systems. And now I work on async networking stuff, and that's almost as interesting. And I can sort of vaguely remember, I think when I started, like when I first downloaded Rust C and started writing like simple Rust programs, I think the @ and tilde sigils had been removed, but that removal had not propagated through like all of the Rust tutorials that you would find like when you Google like how do pointers work in Rust. There would be like all of these blog posts that are like you use the @ and the tilde and they mean things that, you know, and they no longer exist. So that was that's I guess the rough picture of when I first started playing with Rust, and then I've been writing Rust professionally for most of the last 3 years, which is
Awesome.
kind of nice to look back on and realize, wow, it's been a long time.
So you missed the like syntactic merry-go-round days, but
some of them, most of them even.
Yeah.
But I definitely remember, I remember pre-question mark Rust.
Yeah.
Which was, yeah. So I feel like we've come really far since then. And honestly, this is maybe not segueing into your next heading on tracing, but I feel like...
Take it out, we'll go where it goes.
We'll go where it goes. So I was thinking to myself a lot about like, what do I want to talk to Nico about? Because, you know, this seems like a great opportunity to like, just all of my pet peeves and like personal like pet language features that I want, like where's placement new, but that's not really, but I realized, yeah, so like I have a certain, like I'm sad about placement new. I understand sort of why the placement new feature that was on Nightly ended up being reverted, and I think the rationale for it makes a lot of sense, but I'm just kind of sad about it because I feel like that would be nice to have. Anyway, but that's just one of my like pet language features. Where's placement new, Nico? But I feel like there isn't. I think there are a few like obvious holes, but there are also like there's not that much that I feel like is really critically missing from Rust the language right now. Like I feel very happy. I don't feel like we have a lot of the rough edges that we used to have. And I think that like now that async await syntax is stable, we've sort of sanded down one of the last like really sharp, painful, jagged things in the language. And there's a lot of stuff that I would like to see, but or a lot of like what I felt like, as the maintainer of tracing, as a member of the Tokyo core team, a lot of the things that I would like to see the most are sort of ancillary to the language itself, or not directly language features, but are related to things like the standard library, other crates, and even tooling and cargo goals, minus, a couple of sort of key important things. Anyway, that's just sort of my
Yeah, that's pretty interesting.
my setup.
I guess maybe you have a few. I'd be curious to hear a few if there's like bullet points of what you're thinking of there.
Yeah, I think we'll get to most of them. So for me, I think everything, like as I said, I just listened to the Async interview with Carl Erka, who is like the primary or core maintainer of Tokyo. And I think most of the things that Carl identified as being helpful for Tokyo, or that Tokyo needs moving forward, it's pretty accurate from my picture of like what maintaining Tokyo feels like. I feel like Carl brought up, obviously, async trait functions, right? Like that is a big obvious one. And I know that like it's more complicated than just, put the async fun keyword in a trait, right? And it just works. And the stopgaps that we have, like the async trait proc macro that David Tolnay wrote, are very helpful, but that's still like something where there are some rough edges. But and that's obviously a language feature. But then the other sort of core key thing that Carl brought up is the async read, async write traits, right? Which I need to figure out, like, what is the path to stability for async read and async write? And the deepest I feel like that goes into the language itself is, modulo like the design of the traits and what is the like correct way to handle uninitialized buffers and so on, which relates to the language and the rules around uninitialized memory and so forth. But the deepest that the change goes into the language is maybe those traits go into the standard library, right? So it's not really a missing language feature, it's an ecosystem, libraries, and stability feature. Similarly, the other key thing that Carl brought up is what's the stability story? Specifically, he talked about the stream trait, but more generally, what's the stability story for the futures crates, right? And how can libraries that have policies or requirements around stability feel about exposing the futures crate, futures core, or futures util, and so on in their public APIs when there's not super clear stability policy for futures or stability roadmap for futures. And that's really not even, that one really not even a technical issue, it's a people issue, right? So there's a lot of like stuff that, and I like that one I don't see as even like a contentious people issue or a conflict. It's just something that like we need to get down to brass tacks and figure it out, right? And that would be really good.
I want to, that's an interesting question I've been debating about, because one topic, Carl and I didn't talk about it, but in a, as of this recording, not yet published interview, I talked some to Florian about it, and I just talked at other times with others about it. This question of like, so, I mean, it's partly technical and it's partly people, first of all, because the reason people are reluctant to stabilize, of course, is because of technical concerns.
Right.
For sure. And I think there's also like how can we signal the stability question is very important. Even if we decided, well, we're going to stabilize things in futures, and how do we send that signal clearly so people hear it? Because one thing I think is very clear is that nobody really knows. I shouldn't say nobody knows, but there's a lot of confusion out there around what is happening with the futures crate exactly. How stable is it? And I think things like having version numbers like 0.3 doesn't help. Okay. There's a signal to a 1.0 number that just doesn't get sent to 0.3. And also the whole crate structure. I mean, I guess I feel pretty torn about it because I think Taylor has said things like the only real stability is stood, and I think that's sort of true in some sense, but not obviously not the whole story. There's plenty. You don't want everything in stood, so there. And I think we're not going to. I feel like we can get stream async read and async write into stood, and probably in a relatively minor form. And I think if I'm optimistic, I think we could do that this year, and probably relatively swiftly. It seems like the technical questions around them have been fleshed out. What remains is a certain amount of judgment call making. Async read and async write is a little less clear, but I'm hopeful. Yeah. But that leaves, there's a number of other traits in futures, right? And things, some of which perhaps belong in public APIs. And then looking a little bit bigger than that, there are things like the HTTP crate or whatever, right? Which is, it would be nice to have a crate that everyone agreed that you could expose things like HTTP status codes, like an enum for those or something. I don't quite know where that should live. It's not obvious to me that it belongs in stood.
I think, so to me personally, my perspective is that being very deliberate about what goes into the standard library is very important. You know, I have written Python, right? And everyone likes to talk about how a big selling point for Python is that, you know, its batteries included, but not all of the batteries that it comes with are good batteries. There are things where are multiple libraries in the Python standard library that do the same thing, and one of them sort of superseded the other. And when you open the documentation, it sort of says use this new thing instead of this, but it's still in the standard library because of compatibility, and we can't take it out. And so having a small, deliberately curated standard library is good. And being cautious about stabilizing things in the standard library is definitely good. And I think that's something I appreciate about Rust a lot, even more that this is perhaps less of a, a technical consideration and more of just to me personally, something that I have always found very beautiful about Rust, just from an aesthetic sense, is the amount of things that can be implemented in Rust code, right? Even the design of a lot of language features that have keywords or syntax, for example, async await syntax, right, is that it is sugar for code, some of which is, code that's generated that I maybe can't write because it involves generators and so on, but it's compatible with things where there's code that I can express in the language, right? The try trait or what's it called? The unstable trait that hooks into the question mark operator, and before the question mark operator, there was a macro, and we could just write the macro, and you can look under the hood and see how it works. When I was learning Rust, I did a lot of reading the standard library. Because I was learning Rust before the Rust book came out, before a lot of the right now I feel like we have a lot of good content for new users, but when I was starting out, that was less the case. And I found that the standard library was an excellent example of idiomatic Rust code, and it was well documented. And by looking at how things that felt magical, I learned a lot from reading standard hash map. and looking at the way that the borrow and the way that the standard hash map used borrow so that you could be generic over whether a reference to a key or an actual key is passed in to get a value back. And that felt like using the interface felt very magical, but it was very good to be able to sort of peel back and look under the hood and see, oh, here's how this works. And I think that that's a property of Rust that is very valuable to preserve. Both because, to me, it's very beautiful that we try to keep things orthogonal, but also I think Rust is not a small language, right? It's not a list. There's a lot of syntax. There are a lot of language features. And that is a lot for someone to learn who's new to the language, and making the behavior of some of the largeness of the language something where you can still look under the hood and read, here is how it works. This is what happens when I say this. Incredibly valuable. And I think we want to preserve that property. Of course, there are trade-offs in all things, right? And it would be a lot more painful to write Rust without the question mark, without for loops, right? Which is just syntactic sugar for iterators. Be very painful to write Rust without async await. But it's good to hold on to some of the orthogonality, I suppose.
Yeah.
So being cautious about stability is a good thing. And I think it might be helpful if there was just a more public stability policy for the futures crate, which is also a marker of stability. Saying we will if we do a breaking release, we will backport fixes for this period of time, and we agree to do that. And that, in many ways, is a smaller thing to ask than we're going to put this into the standard library, right? Which is sort of once it goes in the standard library, and once it's stabilized, it's in the standard library forever. We can easily go back on that. That's painful to go back on. And I suppose maybe publishing a stability policy for the futures crate is too, but it seems like a slightly smaller step than, we're going to go ahead and we're going to put all of these things in the standard library and they're staying there forever.
Yeah, but there's also a number of, the futures crate has got a lot of stuff in it,
right?
Categories, right? Only some of which the stability requirements don't strike me as equally strong for all of them, right? So the extension traits,
absolutely,
they're more private.
Yeah.
It's the things that show up in your public APIs where you start to get worried.
Yeah.
One example that comes to mind might be the sync trait, which I don't yet fully understand its role. And I think it's at least somewhat controversial. At least, but I don't, and thus I don't know, but maybe it's something that might show up in a public interface where
I can certainly see it being in a public interface. Sorry, was that a network partition? Or were you just
might have been, or might be me just thinking.
I wasn't sure.
But yeah, I guess all I'm saying is I think on those traits, or it would be nice to identify the things that are publicly, things that might need to be publicly stable and sort of move them to, maybe we just want to move it all, but at least those should be declared sort of 1.0, and it should be clearly said, here's how you should expose this if you're going to expose it.
Yeah, I think as a library maintainer, the question is sort of what is safe to have a public dependency on?
Right.
If I have these stability requirements. And even if the answer is none of it is safe to have a public dependency on yet, and that's our published, our stability policy is that we will break these things whenever we want to for no reason. That's still a step further than just having no answer to that question. And, it's better to have something that is known to be unknown than to have an unknown unknown.
Sure.
right? Like this might break at any time. You don't know, but we're going to say that we're saying that we're not going to commit to anything more than that. Anyway, I feel like we've spent a lot of time on this question of stability.
I was going to ask if you want to pivot slightly.
I would be happy to move on as long as you've heard everything you feel like you need to hear from me about that.
I think so. I think this idea of a stability policy actually is not something we've explicitly said before. It's a good idea.
I've been thinking about it because one of the things that we decided, the Tokyo core team decided, I keep saying that word and we haven't really published who that is yet, but we intend to. That's part of our path to Tokyo 1.0. But another big part of the path to Tokyo 1.0 is that we're not just going to, have this big version number. We're actually going to publish like, here are the stability commitments we're willing to make. Carl used the term LTS, right? It's a long-term support release. And we're going to define like, here's what that is. Here's where we will backport fixes. Here's where we will continue to publish patches and so on. Here's where we will probably not have break-in changes for this period of time. And I think that's sort of similar to like Rust 1.0, meant significantly more than here's a version number that has certain Semver implications, but it also means that we as people will commit to certain like additional constraints. Anyway,
okay. Anyway, I think that makes sense. I agree. Yeah, it goes beyond just Semver. It would be helpful, but Carl cited stream. I guess in general, it would be helpful to know, apart from stream async read and async write, what other parts of futures do show up as public dependencies, and then that might be something we can talk about. But,
yeah. I think there is also like right now, if I look at a lot of libraries, I see that most of the futures crate doesn't show up as a public dependency. And I think that might in part be because there's not like a lot of clarity about like what the stability story for these things are. Like Tokyo, I believe has the stream trait as a public dependency, but it's feature flagged. I know Async Standard has also like removed a lot of public dependencies on the futures crate because it may or may not be compatible with their stability policy. So there are things that where like we can look at the ecosystem and say like, yeah, all of these traits show up. And there are other things where we can look at the ecosystem and say, it's conspicuous that these traits don't show up, right?
Mm-hmm.
But
interesting. Yeah.
Anyhow, I'm fine with moving forward from this subject whenever.
There are like two main things I'd be interested to do. One of them would be to talk about tracing.
I love talking
I'm curious about the tracing crate. The other would be, I'd be curious from your point of view as a Linkerd developer, like a side that we haven't heard represented very much, I think, is kind of what makes sense as a person using Async 08. And I don't know if you're the best representative for that. Maybe I should find some more. I'm hoping to go ping around. But like I think I could imagine things like generator syntax move up in importance when you're authoring streams. Whereas if you're, building a framework, it's not quite the same thing. But
yeah, I think that's an interesting question because I feel like I'm wearing a lot of hats right now, right? I'm wearing like my Tokyo hat, my Linkerd hat, my tracing hat, right? And two of those are like library maintainer hats. So I'm gonna talk a little bit about tracing first because I think there's sort of something that sort of fits together here, which is that, so I should probably like do a brief introduction of the tracing crate for whomever is listening from home. So tracing is a set of libraries, a set of crates for collecting scoped, structured, and contextual diagnostic information in Rust programs. A lot of people call it a logging library. I don't like to call it a logging library. And the reason that I don't like to call it a logging library is, The reason that I don't like to call it a logging library is that, like, to me, logging is something that you can do with the instrumentation that tracing emits, right? Logging is, I'm not going to say the word sync, right? Because we just talked about the sync trait, and that is a word that's the name of the trait. Logging is an endpoint, right, for the data that we can collect. It's one thing that you can do with it. We've seen people writing, there's going to soon be a metrics library or an integration with a similar crate that's called metrics. So you can expose like structured metrics based on tracing information you collect. Their integration with distributed tracing systems. Anyway, so it's more than just logging, and it's structured machine readable type data. And the main thing about tracing is it actually came out in many ways of work on both Tokyo and work on Linkerd. And we had this problem, which is that, so as I think I mentioned very briefly in my little intro, that like Linkerd, Linkerd is a service mesh, so it's a infrastructure layer where we have these proxies that sit in front of microservices in a distributed application, and it's a networking proxy layer, so all of the network traffic flows through the proxies, and they do a bunch of different things that make the app better. And we don't have to go into great detail on that, but the important thing about Linkerd in this context is that Linkerd is a very large futures O.1 code base. There's a lot of it. It's very large. It's quite complex now, and it uses Tokyo O.1 and futures O.1 quite extensively. We're sort of beginning the process of updating it to use standard future. This is one of the main consumers of the Tokyo Compat library that I wrote. I was going to say I ended up writing most of it because other people had more important and interesting things to do. So Linkerd is this very large classic futures application. And we had this very bad problem early on in the development of Linkerd that we were using the log crate, and we would log all kinds of stuff that was happening. And we would look at those logs when we were trying to debug issues, and those logs were basically useless, right? Because the core of this async model, right, is that you have these lightweight user space context switches, and they happen a lot, and they happen based on IO readiness, which is not really a deterministic or predictable thing that we can reason about. So you're in this situation where you accept a connection and you open a new connection, to proxy that message to some remote host, and you have these things that are associated, and then you spawn them, and they're running on this Tokyo reactor, and they're just off somewhere, right? And then you accept a new connection, and then you do this again, you accept a new connection, you do this again, and now you have all of these tasks that are running, and if they're all logging like, oh, I saw these headers, oh, there was this IO error that occurred, those things don't happen in the kind of nice synchronous A, B, C, D order that you sort of expect things to happen in a synchronous application, right? So in the sync server, I can say, oh, I accepted this connection, and it was from this IP address. And then I say, a little while later, oh, I got these headers. And I can read that, and I can look at it in order, and I can go, oh, I accepted the connection from that IP. So now we're serving the connection from that IP. And then we get these headers, must have come on that connection. But in the async world, you've sort of lost your ability to reason about things temporally and infer contexts from the orders in which events occur. So we wrote a lot of sort of very janky homemade code. Sean MacArthur actually wrote a lot of it, and so I shouldn't say that it's janky. The parts that I wrote were janky, and Sean's parts were all like very beautiful and elegant. We wrote sort of a hand-rolled solution to this, which is where we had a big thread local, and we would wrap futures so that when those futures are pulled, they stuff some context in the thread local. And then when they're done being pulled, they unset the thread local. And then every log line that happens has all the stuff stored in the thread local put on the front, right? So this is at in a very, very, very like loose sense, this is basically what trace and crate is. But then we had this problem that we wanted to be able to get contexts from, so Linkerd is a consumer as an application, it's a consumer of Tokio, it's a consumer of Hyper, it's a consumer of Tower, H2, all of these other libraries. And so we're adding this application context to all of these log lines. We wanted to be able to have the libraries like Tokio, Hyper, H2, Tower also adding context. But we knew at the time that we absolutely could not just take our hand-rolled thread local context thing and just stuff it into Tokio and Hyper and H2, because those are libraries that a lot of people use. And this code was sort of Linkerd specific. It had a lot of rough edges that, like, for us were not problems, but if it was in every major Rust networking library, probably would have been problems. And it had some opinions that were, again, Linkerd specific that we didn't want to sort of enforce on everyone who uses Tokio. So we wanted to write a library that would work for all of the users of Tokio, of Tower, of H2, and so on, that we could then use to collect this information. And at the same time, we were interested in the idea of like structured logging as opposed to textual logging. So we wanted to be recording machine readable data instead of human readable data. And I guess everything is machine readable with enough regexes, right? That's what a compiler is. That's my understanding of it. I know that's not true. But we wanted to make it easier for machines to read this data because, you know, because there are all kinds of magical things that you can do when machines can read your instrumentation data as well as people. And so that's sort of how tracing was born. I think the key sort of observation of tracing is that in the sort of distributed systems world, there are these tools that are called distributed tracing tools. And basically the way they work in a nutshell is you have these contexts that you report to some trace aggregator, and you propagate them in across network traffics, across different machines. So you say like, oh, I'm serving this request, and then I propagate this trace identifier as a header when I send a request to someone else. So you can see like, oh, this event on this machine kicked off this event on this machine, which caused these machines to do these events, and so on. And I guess the what I like to think of as sort of the key insight that tracing makes, tracing the crate, is that these distributed systems, right? What are their key principles of distributed systems? A bunch of things are happening concurrently. You have these sort of actors that are isolated from each other in some way or another, and they're communicating through some form of synchronous or asynchronous message passing. Normally that message passing is fallible, right? And the network kind of sucks. Well, when you look at the way that large async Rust applications are written, those systems are sort of like those distributed systems writ small, right? Like you have these tasks that are running, and these tasks are sort of a form of actor, and they're sort of isolated from each other, and they're happening concurrently, and they are communicating through this sort of fallible message passing, right? So a lot of the same principles kind of apply in, you know, we have one address space where we have this sort of distributed system instead of a whole bunch of address spaces with network in between. Of course, it's kind of reductive, but like, so, it's sort of the key insight.
Yeah, that makes a lot of sense. I mean,
so that's the background for tracing.
Okay, I want to spit back to you, or I want to put out, like, one reason I've been interested in it is that the Rust compiler, you know, it kind of consists of, you can think of it like, I guess, all these little pure functions, we call them queries. So when I want to compute, type check this function, that's one function, and then it calls other queries to say things like, well, give me the AST of that, give me the here, give me the representation of that function so I can walk down. What type does this function have? What's the signature? And, you know, it's not asynchronous, but it has a similar problem of now you get these random log events. They're kind of occurring. They're not always in the order you want. And for sure, like if you're interested, say, in what happens to a particular function, the logs for that are interspersed all throughout. And so the tool I make the most use of is grep, right?
Right.
Basically how I debug this is just dump a lot of data, find unique-ish things, and kind of grep a lot until
I
I
like
get
to tell people that
merging.
The promise of tracing is that if you ever have to grep through a bunch of logs again, then I've like really screwed up.
Right. So I think you're onto something, I guess. There's definitely a general problem here that is not specific to tracing across machines. So how do I actually use it?
Right. So the way you use it is that you have, we have this crate called tracing core, and tracing core is sort of this facade layer, right? And it's very, very small. It's very light. It doesn't actually do anything. Sort of the secret is that most of tracing doesn't do anything, right? Is that it's a point of interaction. It's an interface. So you have tracing core, and it has the static, and it has some thread locals that you can turn off if you want to. And these store something called a subscriber. And a subscriber is this trait that we have, and is sort of this interface for, here's everything that I need to collect traces. And then there's some core types defined in tracing core, and that's all it does. And then there's another crate, tracing, which is built on top of tracing core, and tracing has a bunch of macros in it. And they look sort of like the log crates macros that we all know and love. And then it also has a macro called span, and span is a little different because span gives you back this span object. And what a span is it's a context. It's saying we're executing in this context. It represents a period of time, has a beginning, it has an end, and then it has some data associated with it. So then you can enter this span handle, and you can pass it around, and you can enter it again. And if you create a new span when you're inside of a span, then you're saying that this span is a subset of that span. And so you can pass these spans around, and they model contexts. And then when you record events with the macros that look sort of like the log crates macros, you're saying like, in this context, I did this thing. And then subscriber is just a big trait with a whole bunch of functions on it that you can implement.
When you make a span, you supply that explicitly to the macros, or is it sort of known what the innermost span is in which you're active?
Okay, so when you use the span macro, right, if I type like span bang, and then I put in like a name for my span and maybe some structured data, what that does is it constructs a span struct that I get back.
So I write something like this. You can see what I'm typing.
Yeah, exactly. So oh, wow, I bumped my computer stand there for a sec. So you get this span struct back. And the span struct has a bunch of methods on it, but the only one that we care about right now is it has a method called enter. Right, and so you say s.enter, and that gives you back a drop guard. And we're about to get into something interesting about that drop guard. But so that gives you a drop guard, and that's saying, as long as this guard is on the stack, I am inside of the span that I just made.
Okay.
And then what happens is that if you say span again, or you say debug or whatever, while you're in this scope where you have this drop guard on the stack, you're saying this event or this span is happening within the span that I entered.
Got it.
You can also, if you have a span handle, you can explicitly say, I want this span to be the parent of some other span that I'm sending off to, who knows what. But all of these things, what they do is they call different methods on this thing that implements this subscriber trait. And the subscriber is sort of like the logger in the log crate, in that it's sort of where you put all of the policy for what do I want to do with this data. So in the log crate, you basically have two methods in there. Is this thing enabled? And then you have this method that is like log this thing, right? And the subscriber trait has a few more methods because it is modeling, it has a much more complex data model. But basically it gets told like we entered the span, we exited this span, we saw this event, and we have some span lifecycle management hooks so that you can have like heap allocated data that's associated with spans if you want to, and so on. And then this subscriber thing gets to decide what to do with all of that information. And then we've implemented a few other subscribers and crates, but it's also where if I want to do some idiosyncratic thing, I would sit down and I would write a subscriber to do my, whatever policy I want to do with this information that's being collected. And that's sort of how the tracing crate works.
Okay. And if I attach structured information to this span, can it get sort of inherited by the things below?
Yeah, so that's sort of the idea is that everything that occurs in a span sort of inherits all of the context of that span. It doesn't it doesn't actually see it, but for example, we have in a crate called tracing subscriber, we have a format subscriber. It's like tracing FMT, right? And that's sort of like a logger. And this logger is going to see every event, and it's going to print out a line for every, like a log line for every event. And what it does is when it sees an event, it's going to look at like, what span did this happen in? And what span is that span part of? And what span is that span part of? And so on. And then it's going to print all of the structured data in those spans before it prints the event that occurred. So you get this little like, and it's line oriented, but you could easily have like very different modes of displaying this. Like David Barsky is working on a very similar thing that waits until all of the spans have completed, and then it prints a nice little tree showing like span, and then this stuff happened in there, and this stuff happened in there. You can't really do that if you're doing it like real time as these events are occurring, because you don't know where to end the little tree, the little ASCII graphics that you draw because they haven't ended yet. So the line oriented one, or the like real time one, is line oriented, but you can make this tree that plays things back, or you can capture like some parts of the execution of the program, hold on to it, and then play them back.
Could you use it? Can a subscriber, like, for example, filter down to certain categories of spans and profiling measurements and not print anything at all?
Absolutely. Yeah. So actually, something else we have right now that John Gangset has a crate. It's called tracing timing. And tracing timing is recording sort of the inter-event timing of of different span and event pairs. And then it makes these like really lovely histograms for you. And so you can, it's a form of profiling. There are people who are working on, you could make flame graphs from tracing data. And the cool thing about those flame graphs, and this is where we get back into async land. And now the flame graph thing is like not done yet. It's something that people are working on. Jane Lusby is working on that. The cool thing about maintaining a sort of core crate to a library ecosystem, the way that tracing is that I can talk about all this great stuff that I'm not doing and say like, yeah, I take full credit for all of this work, which is very cool. It also means that we have a lot of crates.io downloads because there's so many CI builds for all of these things. So I feel very accomplished. But so you can make these flame graphs, and the nice things about these flame graphs that you can make is that your unit is not a stack frame. Because the flame graphs that you get from, if I sample like my futures application, I have these stack frames, and all of the stack frames in my flame graph are basically called pull, right? Like, so I made some big, beautiful flame graphs from Linkerd running, and I looked at those flame graphs and I saw, wow, we spend a lot of time calling a function that's called pull, and we call a lot of different functions that call it pull, and this is meaningless to me. I don't know what's taking up time in my application because everything is just these futures being pulled. But with if I generate tracing flame graphs, every future becomes a unique thing in that flame graph. And we can look at, instead of like, here's the time that was spent in a function called poll, here's the time that was spent in this future that was created in this context. And it's not the only kind of profiling you're gonna want. Like, I don't wanna say that tracing obsoletes CPU profile, right? But if you want to look at what's happening inside of this futures application, this async application, it's valuable to be able to look at what are the tasks in the application actually doing, instead of like, what are the call stacks that I'm pushing? The more profiling tools there are, the better, right? It's not a zero-sum game. It's sort of like they're all complementary, and they give you ways to look at and interrogate different kinds of information. But profiling is definitely a use case, is what I'm saying.
So is your sort of hope or vision, like tracing is not, it's not tied to Tokyo. It's not really tied to async.
Yeah, it's really not.
It's just kind of a way to tag what's happening.
Yeah.
Right. And then have separately orthogonally consumers that process that. If you mentioned something like you wanted to integrate Tokyo into, sorry, not Tokyo, you wanted to integrate tracing into Hyper, or you wanted to integrate something into Hyper logging, but you didn't have a suitable thing, and hence tracing was born.
Mm-hmm.
You feel like if how can I say, it's like let's take like Rayon as an example. Because Rayon starts other threads and moves your work around, and you could imagine wanting to correlate across that. Would the idea be that Rayon could like depend, maybe optionally or whatever, but on tracing and somehow inform tracing that it's about this movement and like
yeah, exactly. So the idea is that right now when I write a program, so like Tokyo used to have a bunch of debug log lines in it, right? Everyone hated them. They were intended for Tokyo developers, right? It would say like, oh, we're polling the ePoll instance that is underlying this Tokyo reactor, and we're looping through these events, and there were 16 events, and it took us, 55 nanoseconds to dispatch those events. And people would complain about them a lot because they would use the log crate and they would set a log filter. They'd be like, I want to turn on debug for my app, and I want to see what my app's doing. And then suddenly it's like, here's Tokyo. I think the particularly infamous log line, the one that I used to hate when I was starting to learn how to use Tokyo, is that it would log on like every 10 milliseconds, there would be this thing that just says Tokyo loop process. And it's like, what the heck is loop process? I don't care. And so these log lines were put in for the Tokyo authors to use while debugging Tokyo. They weren't telling you things that were relevant to your application. They weren't telling the authors of Hyper things that were relevant to debugging Hyper on top of Tokyo. They were relevant to Tokyo. And the goal with tracing, and especially the way that you can encode contexts, is instead of having libraries where they record all of this junk about the internal operation of the library that basically everyone just always turns off, the goal is for libraries to be able to enrich the user diagnostics to say, I say my HTTP server is doing this thing that's part of my like server's actual business logic. Like, I have the cats service and I'm returning a cat picture, and I would say returning cat picture. And when I record that returning cat picture event, I could turn on all of these switches that would then say, like, all I would have to say is returning cat picture, but then it would say, in this Hyper server that is handling this request from this IP address with these headers, with, so on and so forth, and it's HTTP2, and it has these like Hyper things, and then it would say on this Tokyo thread pool worker with this ID, and in this, this task, which was produced from spawning this future at this call site, and all of that information, instead of being like yelled at me that, and sort of, I have to drink from this fire hose when I accidentally turn on give me everything and then tells me all this like garbage about my libraries that I don't care about. It tells you more about what the libraries that you depend on are doing in the service of whatever your code is doing. And it adds context to the events that you choose to record. And like a lot of bugs are bugs that are either caused by library bugs or that are caused by the way that I use the APIs in a library. So it is very useful to know what dependencies are doing, but the information that the dependencies expose needs to be enriching the information that the higher level application or even higher level libraries are exposing, and not just here's what Tokyo did at this millisecond, right?
Yeah. Mm-hmm.
So that's sort of a goal for like what I hope the tracing crate changes about Rust, I guess. I feel like I've spent like a very large amount of time talking about like what tracing does and not all that much time talking about like what does tracing need moving forward. But
Yeah, I'd be curious if you have an answer to that. I mean, what I'm taking away, besides a lot of the details, I think in terms of the implications for the sort of async ecosystem, it's a good example of something that I think wouldn't probably land in the standard library, but which
I don't think
kind
it
of,
should.
right, but which does provide a kind of basic service that a lot of things could, and it would be nice to integrate. I mean, around one of the big concerns is I want us to have kind of a rich ecosystem with a lot of alternatives in it,
Mm-hmm.
but with a lot of interoperability, right, and without a lot of balkanization.
Yeah.
And I don't know, it's tricky at any individual point to figure out, like, does it make sense to centralize on this one thing? Like, should everybody start using tracing, or
right.
basing
So,
out there, which seems like it does a lot less, but I'm not really, I guess I shouldn't say that. I actually don't know. It does similar things in some cases. But yeah, I don't know.
yeah, so the idea of this tracing core thing, right?
Yeah.
Is that it's this like this layer that we can standardize on in libraries and applications. And it, you know, all it does is it doesn't do anything on its own. It provides the synchronization point for if I want to collect this data in this way with these opinions I built out on top of it.
Mm-hmm.
And so I think having that kind of core layer is really good. But the other thing is that, so tracing also has this cool switch that you can flip. And what that switch does is it makes all of the tracing macros also emit log records from the, you know, log with the backticks around it. So it's the log crate and not just log the abstract concept. So it has this switch where you can say like, I want to emit log records. And that's great for like, if I have a library and my users might be using tracing, so they want to collect the tracing events. They might be using logs, so they want to collect the log events. And I, as the library author, don't know, so I can just use tracing and I can emit both. There's also a switch that sort of goes in the opposite direction, which is where, let's say I have a tracing subscriber. I can add this, I actually have a logger implementation, right, that implements the log trace interface. And what I can do is I can set that as the logger in my application. And then it takes any log records that happen and it turns them into traces in the sense of tracing. And so that works in the other way, because you depend on a library that emits log records, but you depend on other libraries that emit traces, and you're using tracing in your application. You can, you know, sort of plug everything together. It just sort of works. And of course, there are downsides to having that kind of compatibility interface. Compatibility layers add more code, more things are happening, and we focus on zero cost abstractions, but, you know, we're doing more stuff. At the end of the day, you're telling the computer to do more things, execute more instructions. But I think that like, this is something where we have the ability to have this kind of interoperability. And I think that it's really good to, you know, as we sit down, we create new libraries, we make new things for people to do, we remember that these, we don't necessarily, it's not a zero-sum game. We don't want to say, you know, the goal for tracing is to end the log crate forever. My goal is that no one will ever use it and tracing will be in the standard library and I win. You know, that's not the goal. the goal is, it would be nice if it was easier to debug your async Rust applications, right? And making these things play nice together is very important. The other thing, and here's where I feel like, here's something that oh yeah, go for it.
Tracing core.
Mm-hmm.
I kind of overlooked when you said earlier tracing core versus tracing, but you mentioned it was a facade layer, I think.
Right.
Is the idea that this is something I could integrate into my libraries and it's like very stable, even as tracing perhaps changes, tracing core will persist.
Okay. There's two reasons that we have tracing core. And I have to credit this idea to Carl Lepke, because he had this suggestion, and at the time, this is back in the days of like Tokyo being split across like 600 credits. And he was like, this is, you should do what Tokyo does. And now, of course, Tokyo doesn't do this. But so the idea of tracing core is that like, the thing about tracing core is that it has one static and one thread local in it, right? And that static is super important. And the thread local is super important. And we can't not have them. And the thread local is what says, here's the current subscriber in this context, right? And if that isn't there, nothing works. And if two versions of tracing core are in your dependency tree that are incompatible versions, there's two versions of the static, and that's pretty bad, right? Because now your traces don't know where to go. And so that's why we took that and we put that in this core layer, and then we didn't put anything else in that crate, basically. It's basically just the static. And the goal is, if we have to bump the semver on it, then that's really bad. But like, we can do it if we absolutely have to, but we want to minimize that as much as possible.
Right, it's a similar split. There's a Rayon core. But one thing that was not clear, so for Rayon, the Rayon core crate is sort of an implementation detail.
Right.
You're not meant to use it directly. Is that also the case for tracing?
To an extent. It's somewhat different. One of the differences is, so we now have this new, like, this is not entirely the case, but subscriber implementations, right? So if I write a library that's like tracing Eliza log, and it emits traces in the Eliza log format or whatever, then I can depend on the core crate and not on the tracing crate. And that's good because it means that I'm not pulling, a version of the tracing core crate that might be incompatible. And I don't really need the macros for actually like instrumenting code. I just need the subscriber crate. So that's one way, like, where you might want to depend on the tracing core crate. The other way is that one of the like little secrets is that it also is the entire interface that the instrumentation API, which is my like pretentious way of saying the macros talk to tracing core. But that's really what they are, is they're a layer of emitting data into the tracing core trace and using the tracing core structs, the types defined in tracing core. So what that means is that if you don't like the tracing instrumentation API, you don't like the macros, you don't like that span names come before their fields, but event format args come after structured fields. If people don't like that, they could write a totally alternative instrumentation layer that would emit the same data model, but would have different APIs. So the user interface could be different. Nobody has really expressed a lot of interest in doing that. I might eventually do it because I kind of like to use procedural macros in some places where we're currently using macro rules macros, and experiment and have like some more like experimental interfaces for users to try out and sort of disrupt myself. And I think that the ultimate sort of, to me, like, this is partially a joke, but I think it's also sort of got a kernel of truth in it. And then I said earlier, to me, like, tracing does not win when it replaces the log crate. I think the one like victory that would make me very happy to see is if somebody wrote a totally alternative instrumentation layer for tracing core that was more user-friendly and easier to use, and people liked it better than the macros that I wrote. And then I could stop maintaining those macros. Because the macros are really bad and I hate them. I mean, they work, they do the job, but like, I
Right.
don't like having to maintain macros. And if somebody came up with like a more elegant, more usable instrumentation layer, I feel like that would be like my ultimate victory here. I would feel very, very proud of myself. And I think this is something that as a community, we can try to design interfaces this way. We can sort of layer the abstraction and make it something that's exposed to the world so that you can plug in different places. And I feel like I'm talking about this in pretty abstract way.
No, but I think that's a key. I mean, I think each place is different, but finding what are these core things that enables everything to interoperate seems very important.
Yeah.
But we're running pretty long. So
Yeah, I'm sorry I
down
just
a
sort
little
of
bit.
like ranted about some stuff here.
No, it's good. It's a lot. There's always more to talk about than there's time to talk about it in. But um, I'm curious whether I jotted down priorities as a Linkerd hacker. I don't know if that was something that sparked. There were particular things you thought,
Well, to be honest, I can't say that much about like using async await in an application yet, or using standard future in an application, because just today I got Linkerd to compile with Tokyo Compat, right? We haven't really ported it over. I think we've learned some lessons from the pain points of classic futures. I think most of those have informed the design of standard future already in the design discussions, that have gone on around stabilizing async await. I feel like Linkerd has relatively little insight to offer here yet. So Linkerd uses Tower, and it uses Tower's service and layer traits very heavily. And one of the biggest pain points working on Linkerd is that I think we have hit possibly a pathological case in type inference, because we have these composed types that are, I think one time I made a type error that was so long that my terminal ran out of like scrollback buffer and crashed, which I thought was very cool. And this also means that like at one point in recent memory, compiling Linkerd took like 30 minutes. We did some stuff. We like basically restructured and rewrote like the whole thing. We split it into a million crates. We stopped returning things, and we started spawning onto the Tokyo executor all of the time as a way of sort of hiding the like very long types and not composing these like extremely long compound types. And we've done all of these we've contorted the code base in some ways to sort of try and avoid the like 30-minute compile times. And it's a lot better now because of these contortions. It still takes kind of a long time to build. And I think, so that's my biggest complaint from working on Linkerd. And I know that like we are just asking the compiler to do a lot of work because we have made these types that are extremely large. And, that's kind of our fault. But we're trying to express some patterns that I think there is a lot of value in being able to express, right? Like, and it's unclear to me whether like Linkerd is specifically composing types in a specific way that is hitting a bug, right, that is causing this compile time. Like if there's some like, or a bug or a pathological case, like if we're causing type inference to be quadratic somehow, or I don't know. You would know this more than I do. Or if it's just that like we're asking the compiler to do so much work that it's reasonable for our compile times to be so long. But I think that's really the one thing that like from Linkerd that I have learned is that it would be nice to, maybe like existentials could help us because we don't have to have these concrete types that are, like tens, hundreds of generics deep. And we can just say, like, so infiltrate in more places. Of course, that has a lot of challenges associated with it. But
default rate is still going to expand to, well, it might help. It would be worth trying to create
yeah, I don't know.
an isolated. It'd be interesting if we can make like a smaller example to profile and look at more detail.
Yeah, that would be nice.
Yeah, I don't know. Interesting. Okay. Well, that makes sense to me though. I've heard other people say this specifically around Tower or Tower.
Yeah,
but
yeah. And I think that like it would be nice if the solution was just like there's an alternative to Tower that's better, you know, that doesn't have this problem. But I think that it's more of a problem with the pattern of when you are, you know, composing a deeply nested set of generics. And like
yes.
a cool thing about Tower is that like these generics are not boxing anything, so we don't really have this like overhead from having like this deeply generic thing. It's just composing the runtime behavior of this thing. And that's like beautiful and great about Rust. You know, we love that language feature. Like Tower is inspired by Scala's Finagle, right? As I know Carl mentioned in his async interview. And we used to write Linkerd1 in Scala using Finagle, and we would be very like, can we put more middleware here to compose new behaviors onto this? Because that's introducing more boxing, you know, because everything is boxed because we're on the JVM. And like, can we pay the performance price of this? We would have these like really bad memory leaks that were just like too many future combinators were used, you know, and those introduce boxing on the JVM because they're all new objects that wrap other objects. And so you just have like all of your heap space would just be pointers to other futures. And we don't really have that problem in Rust because, you know, we have monomorphization. We do more of this work at compile time and just compose the behaviors without paying for it at runtime. Instead, we pay for it when the compiler tries to figure out what's going on. Yes. And maybe that's, I'm kind of happy paying that price, but it would be nice if it was a little bit lower.
I suspect we can do a lot better, but I don't know. We'd have to require deeper investigation.
I wish we had a minimal repro. It's just very hard to have a minimal repro when the problem is sort of like the entire way we have structured our project.
Right. Well, it is open source, so that helps.
Yeah. Yeah. So you can build it if you want to, but that's not a good repro for, here's a specific thing to fix.
Actually, might be. I'll follow up with you about that.
Okay.
It's not going to be as good, but it still lets me look at statistically what's happening, kind of. So.
Mm-hmm.
All right. Let's call it to a close because I haven't.
Yeah, I feel like I took up more of your time than.
But any parting comments?
So I guess the one thing that I wanted to bring up about tracing,
yep.
And about like the other sort of language hole that I feel like it would be nice to have some kind of like answer for, is so tracing uses drop guards, right? And we looked at those drop guards, and I know one of the sort of topics that you wanted to like discuss in the async interviews was async destructors, right? And actually both reached out to me and said like, is this a potential use case for async destructors, and talk about it. And the conclusion was that it's really a totally different thing, but we have a different problem involving async destructors. Involving destructors and async is that like, I think the async destructors feature for like being able to do things like flushing a stream would be great. I would love to see that. It's not actually the thing tracing needs. The thing tracing needs is we use these drop guards to indicate scopes. And the problem is that that doesn't work with async scopes, right? Because, so what we do is like, if you have synchronous code and you have a span, you say like, I want to make the span, you call the span macro, you say enter on that span, you get back this drop guard that sits on the stack, right? And it indicates we're in this scope. When it gets dropped, we've left that scope, right? Futures are not on the stack, right? Tasks are not on the stack. And this is sort of the metaphor I like to use when I explain like what is a future, is that it's sort of like a stack frame that's just sort of loose in the heap. It doesn't go on a stack, it just hangs out until it's done. And what that means is that we can leave a future, enter a different future. The drop guard is still on the heap, right? So we have not indicated that we've left that scope. So a common new user problem in tracing is that people are like, I put, let span equals span macro, let guard equals span.enter in my async block. But now it says I'm in all the spans at the same time. And so because of that, we have a separate way of instrumenting async blocks. We have a future combinator that's called instrument. It wraps the async block, or it wraps the async function or the explicit future that you've written, and it wraps it with a combinator that basically just says, okay, whenever I pull this thing, I'm going to re-enter the span for the duration of the pull, drop it, because pull is like a stackful interface into the sort of async world. But now it means that we have two totally separate APIs, right? And we can't, there's no way to have one consistent API for like stackful code and async await code, because the way that you use the instrument thing is you call like, I have my async call and then I say dot instrument and I pass in a span. And you can't really do that when you call a function, right? Because that's the return value that you're now dot calling on.
So you kind of want some way for things to be, like something on the stack to be informed when it gets yielded, or?
Yeah, and I have no idea if there's like a solution to this. I think the solution might just be every time somebody has this question, we say like, there's two interfaces, async and sync are different. There's kind of this impedance mismatch. It would be nice, because the thing is that like the destructor behavior that we would want for tracing specifically is extremely wrong destructor behavior. We don't want a drop implementation that says when we yield, drop the thing, and then when we resume, undrop it. That
there is
would not be.
Well, it's similar to drop, only in the sense that it seems like a kind of orthogonal trait that you sort of want to be able to add to any type and have it kind of not something you want to like put on your trait bounds.
It's just an interesting problem that I don't know if there's like a solution that makes sense.
I mean, it feels, I don't know where the right trait would be, but it feels like not unreasonable that you could have some callback that you can opt into as when a stack frame where you are on it, when you reside over a yield, you get this callback. It's like a drop callback.
And we would also need a callback when we unyield, right? When we resume from a yield. But yeah, if there was something like that, that would be very cool, and we could have a more consistent API.
You could even imagine it. I mean, it might be. I can't tell. It almost feels like it might make sense as part of drop, but almost not.
Yeah.
You're not being dropped. You're being suspended. It's like a life cycle trait or something. But in that sense, it feels related, because drop is kind of like the end of your life.
Right.
Okay. That's a very interesting. I have not heard that before, but it makes total sense.
I'm not sure how idiosyncratic it is to tracing. I think it kind of is, because we have separate concepts of a span being created and dropped and a span being entered and exited, specifically to deal with like yield resume behavior in async. And I don't know, like,
it feels like anything that's trying to build on thread local may hit something like this. Interesting.
Yeah, so that's sort of an interesting problem.
Yeah.
The only other real thing that can benefit tracing that I can think of off the top of my head is, we're really very interested in procedural macros. And, we have all of these macros that we use for like emitting traces, or sort of like the log macro. And it would be very, very nice if they could be procedural macros, because there are a lot of, much smarter ways that we can parse the input syntax. There are a lot of sort of cool magic things we can do. But these are very commonly called macros, right? Like they're all throughout your code base. And like we are a little concerned about procedural macro overhead. that if we took all of these macro rules macros, we switched them to procedural macros, and because you call them so many times and all your dependencies use them so many times, we made your compile times like 4 times as long. So I think the work that like David Tolmay is doing with Watt is very interesting to tracing. We're sort of looking very closely at that, and also at function, like Carl brought up in his interview, proc macro hack, and how like that's very valuable, but also it's got the word hack in its name, and it'd be kind of cool if there was a way to do this without, you know, a hack. And so procedural macros is something where, and I guess what I'm asking for is really not like any specific thing relating to procedural macros as much as like, I think continued investment in procedural macros is something that like tracing really wants to see. So procedural macros. And then my other sort of thing is that investment in tooling around feature flags in Cargo, and can specifically, like something that has bitten me a lot in tracing is that we want to be able to conditionally support no standard. And feature flags are not really a great vehicle for that. There are some holes in feature flags. And just in general, I feel like the feature flag, doc CFG feature that is on the Nightly compiler now is just incredible, or Nightly Rust doc, I suppose, is just really incredibly valuable in that, like, if you have code with feature flags in it, you can add this attribute and then you generate Rust doc. It actually tells your users this only exists with this feature flag. But another problem that sort of exists with feature flags is that it, unlike crates, it's possible to have almost like code that accidentally works, right? Like, let's say I've written my application and I depend on something from Tokyo, and I don't turn on the feature flag that enables that thing in Tokyo, but I depend on some other crate that does. Let's say, you know, and then that crate might go and change its Tokyo dependency to not enable that feature, and that breaks my code. Yeah. And so, like, we have a situation where an upstream makes like a totally Semver compatible internal, not public API change that is actually a public API change. And it's hard for maintainers to realize the features they enable are public API.
That is a really good point.
And so a lot of people are like very happy about Tokyo used to be a whole bunch of crates, and everyone complained about that. And so we made it one crate that has a whole bunch of feature flags, and everyone's very happy about that. And I think that's a good thing for the most part. But it's also sort of like feature flags have these weird gotchas that crates don't have. And it would be nice if they were easier. It's also very, very hard to test feature flags, especially in a workspace. If you have a workspace with multiple crates that depend on each other, it's easy for them to accidentally enable feature flags globally that you don't realize are enabled globally. There's a very useful and handy tool for testing across feature flags called Cargo Hack. Again, here's like something that's sort of vital to maintaining tracing that has the word hack in it. And it would be cool if Cargo did this itself, but you know, I don't mind the word hack, but it's like, we have a CI run that does sort of a power set of all of our feature flags using Cargo Hack. And of course, this takes like forever because it's a power set. So there's just all of this stuff around feature flags, visibility of feature flags to users, and sort of like maintainability of crates that have a large number of feature flags that I think would be good to continue exploring and investing.
All right, that was really interesting.
Thank you.
Thank you, and talk later. I'm gonna play some.
All right, sorry for taking up so much of your time, but really thank you for the opportunity, and thanks for taking the time to listen to everyone in the community.
Donating so much of your time. All right, talk to you later.
All right.
Thank you, Eliza.